thing that they did on orbit, that the first big celebration. Yeah, it deployed, it was perfect. And it's got to be perfect the first time because, you know, you can't send up the guy to repair it. Thank you so much, Don, for your talk. Maybe we could talk a little bit more while Sam is speaking in the chat. And that brings us to Sam. Introduce yourself and get on with the show, Sam.
Hi. So let me share my, actually, I'm not going to share my screen. Hopefully that will keep the CPU load down a little bit, because when my fan kicks in, it sounds like I'm on a 747. So give me 1 second here. I'm going to share this desktop 2. Click on that. All right. So hopefully you can see the title slide. So my name is.
We can see it.
Let's see here. Okay, and I am off mute. Hopefully, yes, it looks like I am. All right. Let's see here. Okay, there we go. All right, so my name is Sam Falvo, and over the years I've been working on various homebrew computer designs. Never actually gotten one to, well, that's not true. I did get 2 of them to actually get to a completed state, but I was never really happy with them. So my most recent endeavor is to go back to the very first computer that I designed, which originally was called ForthBox, but eventually became known as the Kestrel 1. And so 2024 is coming up, and I figure, well, if I can redesign it and kind of complete what my initial ambitions were with it, it would be a nice 20th anniversary send-off for it. So I'm kind of trying to do my best to do that, but in the process, there are certain things that I need to resolve with the system software, and one of those is, how do I handle asynchronous IO? Now, back in January, I came up with an idea for how to do that, and I'm actually still quite pleased with it. I think it's not even really clever, really. It's actually pretty obvious. However, I do have some issues with it that I would like to either paper over or design out if I can. And so what I'd like to do is I'd like to take this opportunity to discuss how it currently is handling asynchronous IO. Maybe if there's enough time, some of the ideas that I have to address it going forward. So first, what are my ambitions with the ForthBox? Well, I want it to have a keyboard and mouse input, and I would like to use them both simultaneously and therefore interactively. I would like to have background storage access. And the reason why I want that to happen in the background is because the Kestrel 2 computer that I built used SD card access. And when writing to it, occasionally it would take a long time to complete writes. Let's see here. And finally, I wanted a single IO model, something that I can leverage over and over again so that I don't waste my development time writing 15 different IO stacks. So again, why asynchronous IO? Because you can, at least with most Forth implementations today, you can wait on the keyboard or you can wait on the mouse, but you can't do both at the same time. Give me 1 second here. I'm going to jump on mute real quick. I need to talk to someone. Give me 1 second.
Life goes on, even during Zoom conferences.
The single event upset?
He didn't sound upset. Don's talk reminded me of CubeSats, where the processor and communications consisted of actual cell phone, which is a popular alternative for high school students and college projects.
Okay, I am back. I apologize for that. Hello?
We can hear you, Sam.
Oh, okay, excellent. So basically, unless you tie into like another higher level operating system or whatever, you can wait on the keyboard or you can wait on the mouse, but you can't do both at the same time. And as I indicated previously with my experience with the Kestrel 2, writing to SD cards can sometimes range from very fast to unbearably slow. And so I'd like to have an infrastructure to deal with that. So why a single IO standard? Well, like I said, it allows me to focus my efforts better. I spend maybe slightly longer to design the system up front, but on the other hand, it ends up being shorter because I only have to do it once instead of however many times for each IO standard. So there's that. And also it has advantages for technology independence as well. You know, if I want to with the shrinking supply of PS2 ports, eventually I'm going to run out of PS2 keyboards and mice, and eventually I'm going to have to swap over to USB. It would be awfully nice if I didn't have to rewrite everything in order to do that. So the idea back in January was that I would use the 9P protocol as my common protocol to speak with all sorts of peripherals, keyboards, mice, storage devices, video cards, etc. So the idea is essentially the same as USB, but unlike USB, this is significantly more approachable. And the reason it's more approachable is because it is almost entirely described in a small handful of man pages. You can get a working knowledge of 9P by reading 12 Unix man pages. In order to do the same with USB, you need to read thousands of printed pages, at least with the latest version. And now it's true you don't need to conform with all of those thousands, but you do at least need to have a passing familiarity with them so that you know which subsets of the USB standard apply to your application, right? So 9P has definite advantages for being simple. And, and of course it is also compatible with both batch and interactive usage, which, as you saw, is a key requirement for me. The idea of having a single IO model is not new. It's happened at least 3 times, possibly more. Well, if you consider USB, definitely more than 3 times. But it has it is definitely something that has had an impact on the computing industry. But 9P does have its complexities. So it assumes that every user or server for it is concurrent in some way. 9P requests can be extremely long-lived. Consider the case of a computer sitting in a data center in a rack, doing its thing happily for years at a time, right? So the read request for the users for the username or password could take years to be satisfied, right? So that's something to consider. 9P does require the server to maintain state. That is a big disadvantage of 9P compared to, say, rapid IO, because what happens if the server runs out of space? And by server, I'm talking about the mouse or the keyboard. Now, it's true you can get like 16 megabytes of RAM in a fairly small package, but why would you want to have that kind of resources available all the time? And finally, it's a hierarchical namespace, which means you got to have iterators and you got to be able to deal with file attributes and all that other fun stuff. Granted, a lot of this is just static boilerplate, but it has to be there. And so that does add some complexity. But Forth also has its own set of complexities, at least as we commonly know the language today. For example, whether it's cooperatively multitasked or not, Forth uses blocking IO. And so that leads to issues with being unable to cancel a IO request cleanly, right? So here's a definition of key that I've taken from PygMyForth, one of my favorite Forth environments. And as you can see, there's no provision for handling mouse there, right? I mean, the closest you can get is a pause key, which allows you to switch threads. But then it's like, okay, well, if you want to cancel your program, you have to kill all these threads. And there's no way to clean up any initialized state from these threads without doing a lot of behind the scenes work. Finally, there is the issue of changing IO requirements, right? So today I'm planning on using RS-232, or what is known as, more properly known as V.4 communications, to be able to talk with both keyboard, mouse, and backing storage. But tomorrow I might want to do something much, much faster. I might want to use SPI. Well, I have to develop the device drivers for that, and that's going to take time and effort. So it would be nice to be able to develop the SPI firmware right on the machine itself interactively, allowing me to load and unload these drivers, which means that the reliable transport that 9P follows can change at any time, right? So now we're starting to get into operating system level territory here, and we're going to see more of that a little bit later on. I don't think that's complexity that can be avoided, but it is something to be aware of. So, speaking of operating systems, how do we make Forth concurrent while still remaining single-threaded? Now, sub-question, I didn't think to add a slide for this. Why do I constrain myself to single thread here? The answer is limitations are breeding grounds for innovation, right? If you have just a blank page, then you're free to do whatever you need to do. And so you might actually design yourself into a corner. So what I'm focusing on is, how do I do this in the simplest possible manner, which is a very constrained environment. The ForthBox, believe it or not, only runs at 4 megahertz, and it runs on a 65816 processor. So a single-threaded environment for that class of hardware is more than adequate. Imagine a Commodore 64, basically. And the answer to the question at hand is interrupts, and lots of them, right? Which brings us to the idea that we need device drivers. And so we can think of device drivers as software interfaces to concurrently running tasks elsewhere in the system. And there's one tried and true way to implement device drivers, and that's to use what's called a schedule and interrupt approach to handling this kind of concurrency. The idea is that an application would somehow fill out a form in memory and then would schedule a request by placing it on a queue somewhere. And eventually the driver would pick it up, would do whatever is necessary, twiddle whatever bits are necessary to kick the hardware into high gear. Eventually the hardware will, amongst all of its interrupts that it generates, will deliver a final interrupt that basically completes the request. And that driver would set a flag or call back into the requesting application. And this is like if you're familiar with UML, this is like a sequence diagram. I do hide subroutine returns for clarity because they really don't add too much to this. But again, the idea here is that the application calls into some system. The system locates the driver and basically does the enqueuing of the message there. The driver detects this and kicks off the hardware, right? So this is all fairly basic, but in the process, we return back to the application, and now it's free to do other things. So, I could be reading a keyboard, reading a mouse, doing disk IO, and playing music in the background all at the same time. Eventually, the hardware does deliver the final interrupt, which invokes the driver directly without involving the system or application. The driver then responds back to the system that says, hey, the request that you gave me, this is now complete. And oh, look, someone else gave me another request, so I'll kick that off to the hardware. And at the same time, maybe the system software might want to do a callback into an application indicating that the request is completed. This is optional. It doesn't have to be done that way. Most of this is done using message passing, which I'll get to in a bit. In that case, the application then can later basically poll the system that says, give me the next message, and I'll harvest the reply and act on its results accordingly. This interaction, by the way, is essentially how every operating system on the planet today works. So it's not like this is new technology. This is actually quite old. This goes back even to original Unix. So actors and messages are the structures that I use in my version of Forth, which I call System Forth. An actor is a message queue that has a couple of callbacks, which if I have time, I'll discuss later on. But basically, the purpose of an actor is to basically record the work that needs to be done. And the message is just a block of RAM with a predefined layout that all parties understand, including command code. Is it a read or write operation? Where am I reading and writing to? How big is the buffer? That sort of thing. And as this would imply, not only are device drivers actors, but so is your application, right? So when the request is completed, the system, the intermediate system that's involved has to place that reply somewhere. And so the best place to do that is on another actor that represents your application as a whole. And like, as I mentioned, actors do pass messages. Basically, what happens when you send a message in a single threaded environment, it really depends on where you're sending it to, right? If you're sending a message to a program that, just an application program, it doesn't need to do anything because it will eventually query that message later. But for a device driver, it may need to take immediate action. And so that's why I've got those callbacks in. So I have a number of calls or words that I've defined. They kind of do the same thing as system calls that you would find in other operating systems. And they don't take up a whole lot of space, including the core primitives. I'm about 700 bytes compiled. So it's not that much. On average, you're typically dealing with maybe 5 or 6 different system calls, if you want to call them that, at any given time. So it's not like there's a heavy mental burden. So here's an example of how you would read a 1024 byte buffer. We declare the buffer in memory, and then here's our little ticket, if you will, that I call my message. And you'll notice it's got a bunch of fields that are used by various parties, but I reference the buffer and I reference the size of the buffer. And in this, we can ignore this for now. That this is all this ID to actor and unit. This is basically just how to locate the device driver. The real core here is this read block word. So the idea is we calculate a byte offset and we stuff that into my message. We then locate the device driver. We stuff that into the destination field, and then we tell it that we want to read, and that's how we set the command. And then finally, we send the message, and that's what this line does here. Typically, you don't wait immediately for a response if you're going to be doing asynchronous programming. For synchronous stuff, obviously, yes. But the big issue here is if you have multiple things going on at once, who's to say that the response that you're going to get back is related to this message, right? There's really no way to do that. I'm just showing this structure here because this kind of shows you really the bulk of the API that you would be working with. So you're basically dealing with message send, task wait, and occasionally like a cancel operation. So what is wrong with this? Okay, so we know that this approach is going to work, and it's actually relatively clean. It's fairly small, and it is runtime efficient. I mean, all the best operating systems in the world at some level work on this data structure. Well, it still has some issues, right? So there are fragile record layouts. Allow me to illustrate by looking back at this. You'll notice that I have a next field. I have, destination and unit, and I've got these buffers here, right? All of these are pointers in some capacity. And so what happens if tomorrow I decide to use this with a multi-processing environment, by which I mean multiple address spaces? Then these pointers basically are no longer valid because I can't point to a data structure in another address space. what happens if I switch from a 16-bit dictionary space, a 64 kbyte dictionary, to something that's 16 megabytes or greater? Well, then obviously I'm going to have to widen up these fields, and now all the byte offsets, which are located here, will have to change, right? So these are symbolically compiled here, that's fine. But the fact of the matter is, if I take existing code and try to run it on something that has, you know, a bigger message layout, for example, there is going to be the case of, or the possibility that memory corruption could happen because I'm doing explicit pointer arithmetic here. So the other thing is, like I mentioned, it doesn't work with multiple address spaces, which is something that I do want to explore in the future. In particular, my current ForthBox design uses a 65816 processor, like I said, but in the future, I also want to consider using RISC-V together, possibly, you know. So the idea is to have two CPU cards and a backplane both working together. And so this structure of code between them obviously will not work. And then finally, it just doesn't feel like Forth. Like if I'm working with this, it feels like I'm using Forth to code to, you know, some operating system, but it's not. It doesn't really feel like I'm programming native Forth. So what I would like to do going forward, and I haven't gotten there yet, I would like to retain all the original desirable attributes, but I also would like to include some kind of stable interface across both small and large dictionary sizes, as well as involving threads and processes, right? So the idea is to come up with just a general abstraction that's just better for this. And basically that would, I think, make it feel a lot more comfortable as a Forth developer versus someone who's using Forth to code to an OS of some sort. Yeah, I hope that kind of makes sense. That's kind of where I'm at right now. I'm not going to throw away everything that I've done just so far, but rather I would like to find some way of wrapping it or exposing it to a programmer so that this stuff is kept in the background rather than making it in the forefront of an application developer's experience. So that's kind of where I'm at. Does anyone have any questions? Because I know I went really fast with this.
I have a comment. So I was using the 688C11 for all my robots, and I'll tell you, the way I approach multitasking Forth, it was really simple. I just created a counter timer, and it would, when the counter timer overflows, in all processors, you can set up an interrupt register that'll create an interrupt. And then you create an ISR. So if you're doing that 1,000 times a second, you know, you can respond to an external event in a 1 millisecond, for example. And you could do, you could hold your IO in the ISR. And that's what I did, is I created what I called shared registers, and they're just basically, you know, variables. They can be 8-bit, 16-bit, whatever. The ISR reads and writes to IO, and then updates these shared registers. And then your outer loop, you know, your Forth program can read the registers in a, you know, when it needs to. And then you can go back to key, and you can add in the key where, you know, you could add in the mouse and other things in key, so it just doesn't sit there and hang. But the ISR, I also did another thing is, at the end of the ISR, I had a counter, and it would count up to like 100 times a second. So this is just a software counter. And so every 10 ISRs that got triggered, every 10 times, it would call what I call a task list. So the task list is just basically a list of CFAs, and you do a fetch execute on those CFAs. And that task list is cooperative multitasking with your application. whereas the code in the ISR is background preemptive, multitasking. I call it the triune OS, triune multitasking. Have you thought about using something like that?
I have actually. I have recent experience with a embedded operating system that we're using at work called Talk OS. And it's a OS that's actually written in the Rust programming language, but it has 6 system calls, none of which are blocking. And the way that it handles asynchronous events is, it sounds similar to what you're describing, except it's driven from the application rather than from the ISR. But one of the things that it has is a yield function, which basically works the same way as the typical fourth pause function. But what it does is it has the additional feature that it will basically block your application until a callback is invoked or scheduled, and then it'll return once the callback has been serviced, which is a nice way of solving a particular problem that I've been trying to deal with, which is how do I make a concurrency API that is scalable from single threaded all the way up to multi-threading and multiple processes, and it actually seems to work out well. There are other technical design issues with it that I'm running into, but it's more of the issue of, this is a talk related design problem and not so much mine. I just probably need to find a way to just fit it into what I'm working with right now. But yeah, I've thought of some stuff like that, and it is appealing. Okay, if there is nothing else, hopefully I'll get started on thinking this problem through, and with any luck, I'll have a second part within a month or two, and I'll be able to give you a follow-up presentation. And with that, I think I'm done.
Thank you so much, Sam. And I'm looking forward to part 2. Hopefully, you envision that in June?
We'll find out. I make plenty of estimates, and then they just seem to fall through. So
stuff happens. Life interferes. All right. I think that with that, we'll unceremoniously pull the plug on the recorder. So we'll see you next month, all of you. And do give some